Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Yes,
Okay
sir.
then. Electrolytes are the substances that conduct electricity in their aqueous solution are called electrolytes. When we look into the electrolytes, we can divide these electrolytes into the three different groups: these acids, bases, and salts. So let us study about them one by one in detail. First, let us study about acids. Acids are sour in taste. They turns blue litmus paper red. They liberate hydrogen on reacting with metals. Let us look into the examples of acids, like acetic acid, which is found into the vinegar, citric acid, which is found into the lemon, citric, TRI, citric acid, which is found into the lemon, ascorbic acid is also found into the lemon, which is also known as vitamin C, tartaric acid, which is found into the tamarinds. Now we need to study about the types of acids. So types of acid, if you look at, first we have the type of acid which is strong acid. Strong acids on dissolution into water ionizes almost completely. Strong acids when on dissolution in water they ionizes almost completely. There are various examples of strong acids like HCl, HNO3, H2SO4, HClO4, HBr, HI. These all are the examples of strong acids. Then we have weak acids. On dissolution in water, these acids ionizes partially, not completely. And the examples are CS3COOH acetic acid, H3PO4 phosphoric acid, H2CO3 carbonic acid, HNO2 nitric acid, or you can say HNO2 just, and HF hydrofluoric acid. Acidic, all organic acids like acetic acid, citric acid, ascorbic acid, tartaric acid, these all are the weak acids. So please remember that these acids, all organic acids are weak acids. Now let's move and study about the bases. So let's look into the bases. Bases are bitter in taste and turns red litmus paper blue. They are soapy in touch. Examples like washing soda Na2CO3 into 10H2O, then BaOH twice, barium hydroxide, sodium hydroxide, potassium hydroxide, ammonium hydroxide, lithium hydroxide, cesium hydroxide. These are the few examples. Even our baking soda NaHCO3, these all are bases. Now we'll look into the types of bases. First, we have strong base. On dissolution in H2O, when these strong bases are dissolved in water, these bases ionize almost completely. So these bases ionize almost completely. They are known as the strong bases. For example, sodium hydroxide, potassium hydroxide, these are the examples of strong bases. Then we have weak bases on dissolution in water. They ionize this partially. For example, we have NH4OH. So this NH4OH ammonium hydroxide is a weak base. That is what we can easily understand. Now let's move and understand something else. Let us see what is that. Something that is written here. Let us read it. When acids and bases are mixed in the right proportion, they react with each other to give salts. So that is what we have even studied into the 10th standard. But these acids and bases reacts with each other and they produce salt. That is what we need to understand. So now let us study about the salts now. Let's look into the salts. Once again, when acids and bases are mixed in the right proportion, they react to give salts. So then we have salts. Salts are of three types: acidic salts, basic salts, and neutral salts. Let us study about the type of salts. When strong acid react with weak base, they give acidic salt and water. So you can see that strong acid and weak base, Sa means strong acid, Wb means weak base, that gives acidic salt and water. Sa represent the strong acid and Wa represent the weak acid. Same way, my dear students, let's move to the next one, which is known as the basic salt. When a strong base react with weak acid, they give basic salt and water. So weak acid plus strong base, that gives basic salt and water. SB represents strong base and uh, weak WA represents weak acid. WB represents weak base and SB represents strong base. Same way you can understand WA is equal to weak acid, that is what we know. And then we have the next one, neutral salt. So when weak acid react with weak base or when strong acid reacts with strong base, they give neutral salts. So we can write it here that weak acid plus weak base gives neutral salt and water. Strong acid and strong base gives us neutral salt and water. Then I have given you some of the examples of the various types of salts, like HCl, which is a strong acid, and NH4OH, which is weak base. They combine to give NH4Cl, which is acidic salt and water. Weak acid, our carbonic acid H2CO3, and strong base NaOH, they combine and give Na2CO3, which is a basic salt. Strong acid HCl and strong base NaOH reacts and gives us NaCl, which is a neutral salt. Weak acid H2CO3 and weak base NH4OH, when they react with each other, they give ammonium carbonate NH4 twice CO3, which is a neutral salt. So this is how, my dear students, we study about the various types of salts. Now we'll move and study further. Sodium chloride in solid state exists as a cluster of positively charged sodium ions and negatively charged chloride ions. These ions are held together by electrostatic force of attraction. So my dear students, look at this. This is what it is, the sodium chloride NaCl ion. I hope you can see the Na plus and Cl minus ion in this figure. बच्चों आप क्या फिगर में Na plus and Cl minus ions देख पा रहे हैं? मैंने अलग अलग कलर में दिखाए हैं. Please reply.
Yes, sir.
With green color you can see the Na plus, and with the red color you can see the Cl minus ion. So this is what it is, the crystal of your NaCl. Now when you put this NaCl into the water, what happens? Let us try to see. So these are the water molecules, you can see it. So these are the water molecules. We put this NaCl solid, crystal of NaCl, you can say crystal, which is an ionic compound, and these Na plus and Cl minus are held together by the electrostatic force of attraction. This NaCl is kept into the water around the water molecules. What happens? You can see here this is Cl minus. You can see here this is green color Na plus 1. This is Na plus 1. Here also you have Na plus 1. You can see this is Na plus 1. And this is again a Cl minus. So these Na plus and Cl minus ions, they are dissociated, they are brought apart by the water molecules, and you can see that these water molecules are held together, or they have surrounded the Na plus and Cl minus. You can see here Na plus is surrounded by the water molecules, Cl minus is surrounded by the water molecules. Here you can see Na plus is surrounded by water molecules. Here you can see the Cl minus surrounded by water molecules. So my dear students, this is what it is, the dissolution of sodium chloride in water. Na plus and Cl minus are stabilized by their hydration with the polar water molecules. So these ions, when they are surrounded by, when they are covered by water molecules, a special process takes place. That is what it is known as the hydration. So dear students, when these water molecules surround the ions, we call it hydration. You have, and this is how the hydration takes place, and when the hydration takes place, energy is released actually. So hydration of ion is an exothermic reaction, and during the hydration of ion, the energy is released. Electrostatic force between two charges, that is the positive ion and negative ion, electrostatic force between two charges are inversely proportional to the dielectric constant of the medium. So there is one measurement of ability of a medium or electrolyte, which is known as dielectric constant. and the electrostatic force between two charges are inversely proportional to the dielectric constant of the medium. So what happens, the more or the higher is the dielectric constant of the medium, in that particular medium, when you put the ionic crystal, the electrostatic force of attraction decreases. So when you put an ionic crystals into a particular medium or in a particular or in a solvent, what happens, this solvent has got some dielectric constant, and this dielectric constant, the more or the higher is the dielectric constant of the solvent, the more or the electrostatic force of between the ions is decreased to the more quantity or to the higher extent. So we can say that the electrostatic force between two charges are inversely proportional to the dielectric constant of the medium. Medium with high dielectric constant will decrease the electrostatic force between the ions and eventually break them apart and dissolve them. So those ions which have, or those mediums which have high dielectric constant, they generally are brought apart, or the electrostatic force between the ions has been decreased by the medium and or the solvent, and those solvents which have high dielectric constant, they can easily dissolve these ionic compounds. Now we want to study about water, a universal solvent. So water is a universal solvent. Water, a universal solvent, possesses a very high dielectric constant of 80. So thus when the sodium, the value of dielectric constant for water is 80. Thus when sodium chloride is added in water, the electrostatic force between two charges is reduced by the factor of 80. So suppose initially, let's say the electrostatic force of attraction was 800 kilojoule per mole. So when it is added to water, it simply becomes 10 kilojoule per mole, because it is decreased by the factor of 80. So when we divide 800 with 80, we get 10. So this is how the electrostatic force of attraction is decreased by the factor of 80, because dielectric constant of water is 80. As this facilitate ions to move freely in the solutions, and that is what it, as this electrostatic force of attraction is being decreased to a greater extent, these ions of the ionic compound, they can move freely into the solvent. Also these ions are well separated due to the hydration with waters. So once this positive ion and negative ion, you can see here, once this negative ion or positive ion comes out from the ionic crystal, it is surrounded by the water molecules. You can see here, you can see that these ions are being surrounded with the water molecules once they come out from the crystal, and as they come out from the crystals, they are surrounded by the water molecules. This process is known as hydration, and due to hydrations they can be easily stabilized into the solution. So also these ions are well separated, they remain separated due to the hydration with the water molecules. This is how you understand. Now let us understand the Arrhenius concept of acids and bases. So let us study the Arrhenius concept. According to the Arrhenius theory, acids are the substances that dissociate in water to give hydrogen H plus ions, and bases are the substances that produce OH minus ions when dissolved in water. Suppose we have an acid. For acid HX, we write HX aqueous is equal to H plus aqueous, that is hydrogen ion, plus X minus aqueous. But if we write it separately with water, or if we allow them to react with water, or if we write their dissolution in water in a different manner, we can even write that HX plus H2O, that gives H3O plus X minus. Actually what happens, this H plus produced reacts with water, this H plus produced from HX reacts with water and gives us H3O plus. So let us understand it. See, H plus that reacts with water and it gives us H3O plus. This H3O plus, we consider it as an aqueous. This water is liquid, and your H plus which was produced, that was also in the aqueous state. So this is how you can, either you write this reaction or you write these reactions. Both have the same meaning. So if you have H3O plus ion present into the solution, or if you have only H plus ions, these both represent the same thing. Now for base we can write, my dear students, that for base we can write, for base MOH we can write MOH, that gives M plus aqueous plus OH minus aqueous. So this is how, my dear students, we understand about the M plus base that produces OH minus ions. So according to the Arrhenius, acid produces H plus ions and bases produce the OH minus ions. But in aqueous solution, if the salt produces H plus ions, actually it is converted into H3O plus ions. Now hydrogen ion H plus is just a proton. Please remember that hydrogen has one proton inside its nucleus and one electron revolves around the nucleus. Now if you remove the electron, there is only one proton remains into the nucleus, there is no electron outside, and this is what it is, your proton, because only one proton present into the H plus. So hydrogen ion is nothing but just a proton that is very reactive. At the same time, it is very small also. It has got very small size of radius 10 to the power minus 15, and um, it combines with water molecule to give hydronium ion, which is trigonal pyramidal in shape. So my dear students, here I have tried to show you the hydronium ion, which is a trigonal pyramidal in shape. You can see that I have tried to draw a pyramid in which you have oxygen, which is at the vertices of pyramid, and then you have hydrogen. Three hydrogens are bonded to the oxygen, and you can see oxygen still have one lone pair, and due to the H plus ion, when it reacts with H2O, H3O plus is produced. We need to show the positive charge overall. So this is how you can understand the trigonal pyramidal shape of the H3O plus ions. This piece has been detected in many compounds like H3O plus Cl minus in the solid state. So my dear students, if you crystallize HCl some or the other way, in the crystal of HCl you can see H3O plus and Cl minus, because some water molecules also are present into the crystallized HCl. Generally HCl in the crystallized form is not obtained in room temperature. HCl is in the gaseous state. In aqueous solution, hydronium ion is further hydrated to give species like, so hydronium ion again reacts with water. For example, if you have H3O plus and if you add water to it, now hydrogen will become 5, so H5O2 plus. If you add water to it, it turns out to be H7O3 plus. So as this water molecules or as this H3O plus undergoes the process of hydration, and we can get the various ions produced. Even when this H7O3 plus is added one more molecule of water, you can have H9O4 plus. So here you can see that we have a figure of H9O4 plus with us, and here this is your H3O plus ion, which is hydrogen. You can see this hydrogen bonding. This is the hydrogen bonding, this is hydrogen bonding with the three other molecules of water, and thus we get H9O plus 4. Similarly, hydroxyl ion is hydrated to give several ionic species like H3O2 minus, H5O3 minus, and H7O4 minus. Let us understand it. See, if you have OH minus and if it is hydrated with H2O, what you will get is H3, H2 plus 1, 3, O2 minus. Again, if one more water molecule is added, you can have H5, O3 minus. Again, if you add one more molecule of water, you can have H7, O4 minus. So you can see that these are the various um, species that can be also produced when our hydroxyl ion OH minus is even being hydrated into the water. Now this is what it was all about, the Arrhenius concept of acid. Now what are the limitations of the Arrhenius concepts? So Arrhenius concept is limited up to the aqueous solution, because he said that acids are the substances that produce H plus ion in aqueous solution, and bases are the substances that produce OH minus ions in aqueous solution. That means it is limited up to the aqueous solution only. Applicable only to the aqueous solution. So this is the limitation of Arrhenius concept, that it is applicable only to the aqueous solution. Arrhenius concept fails to explain why substances like ammonia, that is NH3, why substances like ammonia, which does not possess OH group, but still they are basic in nature. So um, the basicity of ammonia cannot be explained by the Arrhenius concepts. So that was all. That was about the limitations of the Arrhenius concept. Now we have the another acid-base concept, which is known as the Bronsted-Lowry acid-base concept. So let us understand, my dear students, about the Lowry-Bronsted concept. According to the Johns Bronsted and Thomas M. Lowry, acid is a substance that is capable of donating a hydrogen ion. Bases are the substances capable of accepting a hydrogen ion. So this is how it goes. In short, acids are proton donors and bases are proton acceptors. Consider the example of dissolution of NH3 in H2O. You can see here ammonia is dissolved in water. What happens? NH3 H2O, that gives NH4 plus and OH minus ions. So what happens here? Ammonia NH4 plus adds proton from water and turns out to be NH4 plus. H2O loses proton and forms OH minus. What is proton, my dear students? Proton is nothing but your H plus, because H plus in the nucleus has only one proton, and that is why H plus we call it as a proton. So you can see that water loses H plus and makes OH minus. Ammonia gains H plus. You can see here NH3, it gains H plus and produces NH4 plus. And this is how we understand that NH4 plus has been produced. H2O actually loses H plus and produces OH minus. So this is how the OH minus is produced. So here basic solution is formed due to the presence of the hydroxyl ions. You can see that when ammonia is dissolved in water, it produces the basic solution, and this basic solution is due to the presence of the OH minus ions. H2O acts as a proton donor because it donates the proton to the NH3, and that is why it is called Lowry-Bronsted acid. NH3 acts as a proton acceptor, and it is called the Lowry-Bronsted base. In the reverse reaction, H plus is transferred from NH4 plus to OH minus, and thus NH4 plus act as a Bronsted acid and OH minus act as a Bronsted base. That is what it says, that if suppose the reverse reaction takes place, what happens? NH4 plus reacts with OH minus, that gives us NH3 and H2. So here this NH4 plus donates its H plus to OH minus ion, and thus OH minus ion turns out to be H2O, and as by losing the H plus, our NH4 plus is turned out to be NH3. So by losing the H plus, here NH4 plus donates the H plus, and that is why it behaves as an acid, and OH minus accept the H plus, and that is why it behaves as a base. So by all this we can understand easily, my dear students, that acids are the substances that donate H plus and bases are the substances that accept H plus. So here we get a pair which is known as the conjugate acid base pair. The acid base pair that differs only by one proton, that is H plus, is called conjugate acid base pair. For example, OH minus is a conjugate base of H2O, which is a conjugate acid. So OH minus is a conjugate base of H2O, and H2O is a conjugate acid of OH minus. NH4 plus is a conjugate acid of NH3, and NH3 is a conjugate base of NH4 plus. So my dear students, if you remove if you remove H plus, you get something, that is what it is, base. And from the substance what you remove H plus is actually acid. So this is how we can understand the conjugate acid base pair. A strong acid has a weak conjugate base and a weak acid has a strong conjugate base. A strong base has a weak conjugate acid and a weak base has a strong conjugate acid. Please remember this, that if you have acid which is strong, then its base is going to be weak base. If you have base which is weak, then its acid is going to be strong acid. If you have strong base and then its conjugate acid is weak acid, but if you have weak base, then its conjugate acid is a strong acid. Conjugate acid has one extra proton. Please remember that conjugate acid has always one extra proton and conjugate base has one less proton. So conjugate base you can identify by having less proton than the conjugate acid. Water acts as a acid when it reacts with the ammonia, but behaves as a base when it reacts with the HCl. You can see here that water acts as an acid. Water acts as a base when it reacts with HCl, and it adds proton to itself and make H3O plus. That is why water here accepts proton and that is why it is base. But the same water, when it reacts with ammonia, it gives proton and turns out to be OH minus, and that is why here, as compared to ammonia, water is acidic, but as compared to HCl, water is basic, and thus water behaves as a both acidic as well as basic in nature, and that is why we can say that water is amphoteric in nature. Amphoteric means the substance that behaves as acid as well as base and reacts with both acid as well as base, and thus water is amphoteric in nature. So my dear students, when we look at water and if we add one proton to it, we will get H3O plus, which is a conjugate acid of water. But if we remove one H plus from water, we get OH minus, which is a conjugate base of water. So water can have both conjugate acid as well as conjugate base. I hope you understand, my dear students. If you have any doubt, you can ask me. What would be the conjugate bases for the Bronsted acid HF, H2SO4 and HCO3 minus? So we want to find out the conjugate base for this species. My dear students, to obtain the conjugate base, we will have to remove the hydrogen H plus ion from them. You can see that all these species, these two species are neutral. So when you remove the positive charge from them, you will get the negative charge. So when you remove the H from HF, you will get F minus 1. When you remove the H from H2SO4, you get HSO4 minus 1. Now here when you see, you have HCO3 minus, but you remove one H plus, which is plus 1 charge. So this negative charge become minus 2, and you